Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to this next lecture in this particular series particularly on these aspects of the microscopy aspects of it that we have been discussing in the previous class. The microscopy aspects, particularly in the atomic force microscopy that we have been looking at. Let's continue with these atomic force microscopy aspects. And we have looked at the basic concept, the basic principle, how this is being functioning, and in fact this can be used. The variety of applications are there. So the applications in the solid state, semiconductor technology, molecular engineering, polymer science, polymer physics, chemistry, etc., surface science, surface chemistry, surface biology, molecular biology, cell biology, medicine, everywhere. And in the solid state physics, one can look at these using these techniques, the identification of the atoms at the surface, particularly evaluating their interactions with a specific atom, neighboring atom, study of the changes in the physical properties arising from the changes in the atomic arrangements, etc. So entire level of solid state physics aspects of it. In the molecular biology side, if you look at that, in the molecular biology side, you can always look at this in terms of the assemblies, protein molecular interactions or protein surface interactions, or small molecule with the protein interactions, all of these, where microtubules, etc., all of these. In the cell biology, you can also use for that. You can understand the cells by touching these ones using the AFM kind of a technique, the softness, hardness, these kind of things, and which differ because of the nature of the cells, the normal cells, the cancer cells, etc., all these kinds of things. So, or you can also study by modifying the tip of the AFM, the tip with certain kinds of molecules. You can study their interactions on these cell surface as well, okay, because they will have the receptor sites. So that kind of the complementary groups, if you can modify the cell surface, you can also, so therefore you can map those kind of things as well. And you can use in the electrical potential variations by conducting the cantilevers. So, and you can use for current measurements as well, okay. So electrical conductivity, current, transport, all these kinds of things. So you can use for the folding, unfolding the proteins in these kind of things. So variety of aspects, variety of phenomena in biology, in physics, solid state physics, and in chemistry, and everywhere you can use. So cell biology and electrical kind of things, etc. So therefore the application domain of the atomic force microscopy will be there everywhere. We've already looked at how this principle is working in the previous class, and now we will look at the aspects relevant to that in terms of the types of the forces and the modes of imaging kind of things. And you have seen earlier that you have a tip which is referred as the cantilever, and this is made up of either silicon or silicon nitride with a tip which is in radius of the few nanometer size. So that means this tip is the one contact point to the surface of your compound, layer, or whatever that you have. So that is a contact through the nanometric level contacts that. Okay, and then you look at the forces between them. So between the tip and the surface. Of course, in the modern days, even the tip has been modified in the past several years, and therefore modified tips are also there. So you can coat with certain kind of a liking things, etc. In biological ones, you can have the antigen antibody kind of things, etc., or the enzyme substrate kind of things you can modify, or something that which can interact. So a lot of modifications are also possible on these tips, and then can be used. So basically you're looking at the force between the tip and the sample, and that leads to the deflection in the cantilever, and so that is where you study. So these are the kind of things hope you're looking at. I'm just showing some factors on the slide, though it is not a figure, and there is some these forces between the tip and the surface. Okay, so these mechanical contact forces, van der Waal chemical kind of a forces, capillary forces, chemical bonding forces, electrostatic forces, some magnetic forces. So all these kinds of things can be there between the tip of this AFM and the surface of your material, which is taken as a thin layer or something of that kind. So this will affect magnetic forces, solvation forces. So these quantities may simultaneously be measured using the specialized force probe. So scanning, thermal microscopy, scanning, Joule expansion, photothermal, so all of these. So all of these come under the huge basket of the atomic force microscopy measurements of this. Okay, so this can be operated in a number of ways depending upon the application. So the possible imaging modes are divided into static, the contact type, and the tapping type. So where you have the micro tip of the cantilever grazes the surface. In the other case, it is just going through the kind of a forces but does not touch completely the forces. So these are the two major kinds of the things where one uses for the imaging purpose. Okay, so let us look at those two kinds of major kinds of the imaging purposes, imaging methodologies. So one is called the contact mode, and which is basically there is a contact between the surface of the sample and the probe tip or the cantilever tip, you can call it as either way, and the other case as a tapping, so keeps moving up and down, etc., and because of the forces that are there between the sample surface and the tip, and you can measure these things either by feedback loop mechanism or by the deflection. You can use either of those techniques. So variety of these techniques have been very well developed in the literature and people use. Let us look at one of them, which is the contact mode. This I've already explained to you earlier. This particular, yes, I've already explained to you here how the AFM in principle can be functioning. So now we look at using that as the basis. We look at that. So you can measure the XY and you can measure the Z axis as well. You can change the Z axis. So you can have the movement of this, and this is the cantilever and this is the probe part of it. And so what you basically is, I have already shown you that it is, you shine the light and then the light deflections you will measure depending upon how it is moving on the surface. You can see this is basically the sample and this is the surface. This whole thing is shown in one dimension. Then you have two dimensions and you have three dimensions. So the X, Y, and Z, all the three dimensions that you will be able to measure in these ones. So you can scan along with all these. So by using different motors, you can move these, and the probe can be sitting but then can be moving on this. Or you can also alternatively, the cantilever will be moving and you can have a this stable platform on which can go up. Both of these can be in mobile form of it. So in this cantilever, in this contact mode, then you have this moving on the surface of your pound, and these light changes, deflections are being measured and converted into the current, and then this is being used. In the other case, in the tapping mode, it will not be touching the surface. Okay, so there will be again a loop here to make the cantilever deflections coming up and down without touching the probe, and can be moving on the surface in all directions. So that is the kind of thing where you have the tapping mode. It will not touch the surface basically. So it will be coming closer and going farther, going closer and farther, depending upon the kinds of forces that you have. So it will avoid grazing the surface. It will avoid making any kind of the surface scratch kind of methods, but still such understanding the whole surface. So remaining aspects are same, the IV, the differential amplification, etc., amplitude, everything. The only thing is you have a loop here which gives the feedback to move on this, and either you can move the deflections or you can compensate the deflections by the circuit, and then see how much you have compensated all this. So one is called the referred as the contact mode, some kind of a grazing the surface. The tapping mode, which is coming closer and going farther, coming closer and going farther. So wherever you have attractions, they come closer. Whenever is a repulsions or less attractions, go farther, and therefore you get the topological, all this. So this is the kind of a thing that you use in this, and you can use both. In case of the tapping mode is the better preferred, because will not make much kind of a problem either to the tip of the cantilever or to the surface of your layer of the specimen as well, both ways. Okay, so let's look at this particular slide in the contact mode, and this is basically a contact mode, means which will drag along the x-axis, y-axis and z-axis at its particular kind of a speed, and then measure these deflections and then make the mapping. Okay, so that is across the surface of the sample and the contours of the surface are measured either using the deflection of the cantilever directly, or more commonly use the feedback signal. I mentioned both of these to you, either from the deflection or for the feedback cantilever, to as if you're using it a constant, so that you use that one. So the measurement of a static signal is prone to the noise, and these are of course noise and drift and the low stiffness of the cantilever, okay, are used. Okay, so close to the surface of the sample, attractive forces can be quite strong. In such cases, when the forces are strong, then this tip can go and snap in. The tip can go and snap in to the surface. So therefore, contact mode almost always done at a depth where the overall force is repulsive. Will not be of that. Otherwise, you will have the tip getting ruptured, tip getting bent, tip getting dent, etc. These kinds of things can happen. So if in the repulsive thing, it will not get attracted, not get snap, tuck, snap kind of thing. So it will be out. So you use more of a repulsive range rather than the attractive range. This is confirm the contact mode with the solid surface. So this particular picture here, as you can see from this has the 5 micron the range here on this, and then again 5 micron. So the 5 micron by 5 micron, and with a 0.14 micron in the z direction. So this is, you can call it as a depth, and this is your area. So that's where. So AFM topological scan of a glass surface. So this provides the micro and nano features. You can see in the on the surface how these because this is a glass does not have a crystallinity, we have a local structures, and you can see the local surface structures of all these things. You can be measuring in this through a contact mode, set whatever. The other method is the tapping mode, which will not touch the surface, and this is most now commonly used for many of the samples. It goes up and down at certain kind of a resonance frequency. So using some kind of electrical signal, piezoelectric thing, you can use these ones. So cantilever or a periodic heating, variety of things can be. So the amplitude of these oscillations are generally within a few nanometers to about the 200 nanometers or so is the tapping mode. It will not hit as such, but it will come closer and goes away, come closer and goes away in this. So that is where the thing is that. So the frequency and amplitude of these signals, if you can kept constant, then you can see the feedback signal, or you can look at the deflections and you can measure. So these are the things. So what kind of things? Of course, just like I already explained to you earlier in the previous class, these forces, the cantilever tip feels the forces of the surface. So the van der Waals, dipole, electrostatic, variety of these kind of things. So extent of force will be the extent of the displacement, the amplitude of this cantilever. So oscillation to change, and as the tip gets closer to the sample. So these are the things that, so that will give you the going away, will give you the elevation of that, coming closer, those gives the elevations of that, and moving across will give you the on the x y map. So you'll get both the xy map and as well as the z map. So xy and z. So certain level of thickness can also be measured from AFM, and so that is what is coming from the z axis, and of course the xy area of that. So here you can see an example of this is the plasmids, DNA plasmid structures at different, the two panels are shown here in this particular slide. Kindly draw your attention. So the plasmids which are somewhat open kind of a plasmid at 3.89 pH, and somewhat closed kind of a plasmid at 4.24, which is more less acidic than this, and you can see their morphologies, etc. You can see how their structure. So these are, this scale is around 25 nanometers, so whole thing that you can see all of these. So you can see the depth parameter from these ones too. Okay, so that shows the color levels will show the depth of it as well. So you can get the overall mapping of this, the imaging of this, and with the depth levels by color contrast that is shown, and the of course X, Y, Z. So this is basically the tapping mode. They will produce the force of intermittent. So the tapping mode generally lessens the damage because it does not touch the surface or sudden jump into the surface or go out. These kind of things are not there. They maintain certain distance but feel the interactions through these, and those interactions are measured through the feedback mechanism or the deflection mechanism, or both, depending upon whatever is used. So tapping mode imaging is gentle enough even for the visualization of supported, for example, lipid bilayers or absorbed layers on a scale, where you take some solid support and put some kind of a layer for doing some catalysis, some polymer things, for some embed some kind of a matrices, use the polymer as matrix and put some other components for certain property like conductivity or magnetic or those kinds of things, etc. Then you have a layer. The layers can be studied up to certain kind of a thickness. So you can see that. And if you have something liquid surfaces, you can do, or some kind of a layers which are meant on the surface of the liquid, and these kinds of things can also be studied by the tapping mode. So with proper scanning parameters, the conformation of the single molecules remain unchanged for even hours. They are not going to hit the molecule as such, but they are still getting the feel of those things. So the single molecular motors, all these things can be imaged by using the tapping mode as compared to the contact mode. The contact mode can make a kind of a grazing, can make some kind of a dents, can spoil the tip of the cantilever, tip of the probe. All of these are possible, whereas that is not so with the tapping mode, and tapping mode can be. So you can use for variety of fragile biological samples, you can map, image, etc. upon these things to a nice atomic nanometric level resolution of this. Okay, to understand that we need to look at certain kind of examples. So let us look at some examples of this. So these examples I'm going to cover only up to the microscopy level, but the papers will have many other data as well. We will not be going into those aspects of it. So because the microscopy is used for basically for the characterization, whatever we claim is there, whatever is there can we claim. And then for further properties, we are not going into the things, but the characterization itself will tell you what is there. For example, here I draw your attention to this particular slide, the AFM evidence for the formation of nanocomposite of graphene oxide filled ethylene methyl acrylate, EMA. So ethylene methyl acrylate is a polymeric material into which you put the graphene oxide, so you're making a nanocomposite of this. These are the AFM images at the 4 stages. One is at this particular the polymer with 1% of graphene oxide, and the B is with the 3% of the graphene oxide, and the C is 5% of the graphene oxide, and the D is 7% of the graphene oxide with the same ethylene methyl acrylate. Ethylene methyl acrylate forms the base, your polymer material, and then in that you put the graphene oxide, then it becomes a composite. Now, what is that you are studying? You are studying how well it is dispersed, what kind of a surface smoothness, roughness you have, how the distribution of these things, how homogeneous, how heterogeneous. So the distributed regions, what the properties of these distributed regions, these are the things that what you measure, and that's what you're looking at. If you look at this, very little, obviously 1% only you have made, you can see that 1%, so therefore not so much of a distributed. You make 3%, a little bit better, but when you go to the 5% of this, you get a very nice distribution, the somewhat very good level of homogeneity of the distribution of your graphene oxide into your polymer. And if you go beyond that level, again these graphene oxides will start folding. You can see the folding layers of all these things, and so therefore the effect will not be very good for the properties what you are looking for. So you can identify using these AFM microscopy pictures of this. So what is the best composition level of this the composite, and so which will give a better properties. Later on you measure the properties, etc. So in this case, this is the roughness of this 5%, is this film varies between 13 to 15 nanometer, large continuous area. So it's a very homogeneously kind of a thing. So if you go to the D part of this, where you have a 7% of the loading of graphene oxide is there, so you have a lot of particles, aggregations have taken place. Here is it distributed very well homogeneously and very distributed evenly, you can call it as, and whereas here is distributed unevenly, and because of a lot of aggregations are there, and the roughness goes much beyond 24, 26, whatever be the levels. So that is the kind of things. Here the roughness is somewhat limited kind of thing, and distribution is very good. Therefore you can identify, you can select what are the best nanocomposite that you can use for further studies, for further properties. So these are made for certain things. So these microscopy will help you to choose the best samples. Of course you can take the somewhat worst sample and also check those properties, and you will know that the properties are not good for those kind of things. So that is where you have. So I hope you understand this example of that, the 4 levels of loading and the corresponding things, etc. So nice, very uniform distributions of all these things, and the very optimal levels of the roughness, everything is quite well, but beyond that and below that. So below that is also not very good, distributions are not even, distribution is not sufficient enough, and the roughness parameters are different, and therefore you have not so much of use. So you can select the samples which are good for further studies, and then you can make a backward comparison between the property, whatever you're measuring, versus the surface structures of these things. Okay, let us look at another example or application of this. This is the silver nanoparticle, AgNP silver nanoparticle as nanofiller for chitosan. Chitosan is the polymer matrix to increase its thermal stability. In this, I will not talk about the thermal stability, but this material is used for the thermal stability by impregnating the silver nanoparticles into the chitosan. So chitosan is a polymer into which you can. So this again the AFM study. Draw your attention to this particular slide, and the A is just the simple silver nanoparticle. B is the chitosan and this nanoparticle put into that. The C is the embedded nanoparticles into the chitosan, and the D and E are the corresponding 3D versions of it. So 3D views of the chitosan silver nano composites, and the F is the topographic features of these ones. Okay, so you can measure these topographic, that means the elevations, the ups and downs of these. So in other words, the surface contours with the z direction parameter. So from here you can get the z direction parameter, which is the roughness parameter also, which is called. So you can get the roughness parameter, you can get the how this is distributed, and you can restrict the range, you can expand the range and study all of these kinds of things that you can do very well. Okay, so in this case, the chitosan nanocomposite film reveals predominantly hill valley structured surface with irregular pores of nanoscale topography. The surface roughness measured and the scanning areas, these ones, is around 5 by 5 micron, is estimated to be 2 nanometers and 5 nanometer for pure and the nanocomposite. So the nanocomposite is showing 2 nanometer roughness and the composite is showing the 5 nanometer, which means the composite definitely had the other, that is the AZ nanoparticles being embedded into that, and that's you can see always. And the area is done is 5 micron by 5 micron, the slice or area in that. So you can focus using the AFM that region and study, and that's what is 5 by 5 micrometer. And the 2 nanometer, 5 nanometer is 2 nanometer is for the just the polymer chitosan surface, and the chitosan plus the silver nanoparticle is the 5 nanometer. That means silver nanoparticles got embedded into that. So the topography patterns of the nanoparticles comprised of the heights from 0 to 70 nanometer and the side lengths ranging from 1.5 to 4.5. That is where the regions are that. Okay, so thus this clearly shows that the size of the nanoparticles are much less than 100 nanometers in the chitosan matrix, and it also gives the distribution, and thereby you can utilize for the property measurement. Here is a thermal stability, and you can vary this composition again study, and therefore you can identify the maximal or optimal kind of thing. So therefore the AFM will help you to prepare the samples to help what level of these things are there. I hope you understood. Basically this is a characterization kind of a technique before you go for the further measurements of that. Okay, so come to the another example of this, the AFM. This is for the carbonaceous nanoparticle, carbon-based nanoparticles in epoxy. So the TBD epoxy, the nanocomposite. So this nanocomposite is used for the aeronautical applications. So obviously the composite surface structural parameters are very important for expected performance when used in the aeronautical applications of that. So this is the for the 3% of the exfoliated graphite sequence of this, and this is for the carbon nanofibers. So these three are for the carbon nanofibers of 1%, and these top three are for the exfoliated graphite. So your nanocomposite epoxy, the epoxy nanocomposite is referred as TBD, and then you have a 3% of the exfoliated graphite, and this is basically the carbon nanofibers. So two different types of materials here. This is one kind of a nanocomposite, this is another kind of a nanocomposite, and these are studied for the height and for this amplitude, and this is for the phase. All the three kinds of things are being studied. So this is for the top one for the this exfoliated graphite, and this bottom one is for the carbon nanofibers, and these level of the depth is shown by the color levels are these ones. As you can see, the nanofibrils here and the exfoliated graphite distributions, so shown from the height, shown from the amplitude, shown from the phase. So the same kind of things. So this height will give in the nanometer, the amplitude is giving in terms of the millivolts, and the phase is giving in terms of the degree. So you can see the degree wise, millivolts wise, and the nanometer wise. So that is the kind of things. So you can see that these samples, the kind of a distribution of these things can be understood, the how finely, how uniformly they distributed these, in this case nanofibers, in this case exfoliated graphites, and their concentrations, their depths, their profile in terms of the roughness, all of these can be from the height, from the amplitude, from this the phase. So this can give you the image in the x, y, and z directions. The amplitude, either you can use the tapping mode or the deflection by contact mode. Most often tapping modes are more used. Change in the oscillation amplitude by the AFM to trace the surface. So one can be used for the shape, the other can be used for the surface, the third can be used for the strength of that thing, elastic of this. So you can use for this, for the elastic. As well, it can be used for different phases. So when you make this particular kind of a composites, are there some phases stabilized in this, new phases formed? All of these can be studied, all the three, from three different kinds of images. So these give you, so AFM technique through the capture of height, topography, amplitude, and phase data simultaneously allows the surface structure and material domains to be directly compared. In conclusion, the AFM morphological investigation demonstrated that the good levels of, in this particular example, carbon nanofiller dispersion into the epoxy mixture improves the properties of nanocomposite and also the curing process, etc. Therefore, these materials are passed for their composition, then can be taken to the next level of these things. Okay, we will look at a few more examples or applications of the AFM in the classes to come, in the next class or so. Thank you very much.